us 3 lectures tonight, today and the next 2 days on, gosh, that's a nice new title, The Mirror of Mathematics.
Thank you. So first of all, I'd like to thank the organizers for inviting me to this event. It's really wonderful to be back in Oxford. I've spent 2 years here, but spread over almost a decade, and I've seen people like Jamie grow up from infants to young people. So today's lecture, and in fact my whole series, is not so directly connected with quantum mechanics as the preceding lectures. It's rather more mathematical, but it's a piece of mathematics that I've been very attracted by the last few years, and I've spent some time working on it. And I really find it beautiful. I use this phrase, the mirror of mathematics, for reasons that I will explain presently. So there are 3 kinds of dualities that I will talk about. Today is sort of classical stone-type dualities. And tomorrow will be Gelfand duality for commutative C-star algebras, which is somewhat more closely connected to quantum mechanics. So really, people who are interested in quantum mechanics are interested in the non-commutative case. And finally, I'll talk about Pontryagin duality. And just to complete the full spectrum of name dropping, I'll end with Tanaka duality on Wednesday. Right, so can I get
down? Just down.
Down. Ah, down. Okay, down is up.
Down is the new up.
Down is the new up. So just a quick outline. I'm going to try and describe the general notion of dualities. Work through 3 specific dualities, the ones that I mentioned: stone, Gelfand, and Pontryagin. And what I'm not trying to do is to review all possible dualities, because there are millions of them now. In particular, this afternoon, Bart Jacobs will start a series of 3 lectures on Cadison duality, which is closely connected with the theory of stochastic processes. And unlike me, he will be doing the mathematics in some detail. Mine will be very much an overview. Anytime it comes to something difficult, I will heavily skate over it and only indicate perhaps some of the ideas. I'm definitely not going to talk about my recent work on automata theory, where I used duality to minimize automata, nor am I going to talk about my other work on duality for Markov processes. I'm definitely, absolutely not going to prove everything in detail. Indeed, I'm not going to prove anything at all, if I can help it. Nor will I discuss the connections to physical issues. But let me get back to the issue and say something positive. What am I going to talk about? So there are many dualities that one knows. Perhaps the most elementary one is the duality between and or in propositional logic. So this is, of course, De Morgan duality, and perhaps one of the first that one is exposed to. So of course this word duality has not even been defined yet, and I will come up with a more precise statement of what I mean. But these are meant to be suggestive examples of duality principles. Computer scientists, of course, see duality in linear programming, where they are taught that there are certain maximum principles that correspond precisely to certain minimum principles. And this is a beautiful duality, because it tells you you're trying to find something by maximizing a particular functional subject to certain constraints, while it's the same as minimizing something else with respect to some other, in fact, somewhat dualized constraints. And the beauty of having both these views is that you can use one formulation to give you upper bounds, another one to give you lower bounds, and if you're clever enough, you can squeeze these 2 inequalities to prove an equality that neither one alone could do. And this is the essence of this whole duality point of view. You have 2 ways of looking at things, superficially very different, but you see that they're actually different views of the same thing. And that's what allows you to do more powerful things than either one view could do by itself. In physics, there's a duality between electric and magnetic fields in the Maxwell equations. And this has been beefed up in more modern physics to something called geometric Langlands duality, which is connected with something else called S duality, neither of which I understand. But as I said, I'm fully in the name-dropping phase now. In the late 50s and early 60s, there was a kind of duality imported from linear algebra to control theory, which is the duality between controllability of a system and observability of a system. And this is associated with the name of Kalman. And in fact, this Kalman work on automata theory that I'm not talking about. People in programming language semantics are familiar with the duality, though it may not be presented to them as a duality, between so-called state transformer semantics and weakest precondition semantics for programming languages. So in state transformer semantics, you're given the state of a system and you're trying to explain what a certain programming construct does, and you do it by saying, this is how that construct will transform the state. By contrast, the weakest precondition semantics says, if I tell you a certain property of the state at the end, what must have been true before? You see, it's kind of a backward flow and it's going in the opposite direction. That's why it's called the weakest precondition semantics. And of course, there is this nice correspondence between them, first explained by Jaco de Bakker. However, it was Gordon Plotkin and then subsequently Smith who explained it as an instance of stone-type dualities. So this is another duality that has been important historically. And indeed, kind of corresponding duality in data flow analysis also exists, where you have backward flow and forward flow, where you're reasoning about properties of programs doing static analysis. There is, of course, the duality between induction and co-induction, which is indeed another thing very popular in computer science. Induction is typically associated with algebraic structures. Co-induction is associated with co-algebraic structures. And one describes the structure of a system, the other one describes its behavior. So there's a nice duality there as well. So everywhere we see these kinds of things emerging. Now, so what is duality intuitively? So we have two kinds of structures, foo and bar. I used to call them vish and shiv, but I decided not to use such emotionally charged words anymore. So foo and bar, two kinds of structures, made up names, doesn't matter what they are, but what is important is that you have a way of constructing from any instance of a foo an associated bar, and vice versa. So you have these two mathematical universes. Every time you have a gadget that lives in one of them, you can construct something that lives in the other one, and you can go back. So you can go back and forth between these two worlds. So what happens if you start from one of these foos, you construct the corresponding bar gadget, and then you apply the vice versa construction, you get back another foo. How do those two relate? Well, if you have a nice duality, you would like to actually get back to something that's isomorphic to the thing you started with. Okay, so you can go now back and forth and return to where your starting point. That's what's telling you that you have two different views of the same thing. So these two apparently different structures are actually two different descriptions of the same thing. And furthermore, something even more important happens. It's not just that you can take a gadget and construct another gadget and go back. It's also something that one can do with the maps between the gadgets. So if I have two foo objects and I have a map between them, something that preserves whatever this foo structure is, perhaps you can call it a foomorphism, then not only can you get the corresponding objects in the other world, you also get a map in, however, the reverse direction. You see, this map went from S1 to S2. Corresponding to S1, you have a V1. Corresponding to S2, you have a V2. But the map goes in the reverse direction, from V2 to V1. And again, this is also in both directions. So starting from maps in this world, I can get maps in the other world, again with the reversal. Okay, so this is crucial. Note the reversal in the direction of the arrows. And that's why I use the phrase mirror image. Okay, so there's this mathematical universe described by this web of objects and morphisms connecting them. And then there's this other picture of it which looks just the same, except everything has gotten flipped. Okay, and this flipping is a crucial part of it. It's what makes one the mirror image of the other. And the important point, just as I illustrated with the case of linear programming, is that you have two completely different sets of theorems that one can use. So typically you have dualities between some kind of algebraic world and some kind of topological world. And sometimes you can do something using your algebraic structure. At other times you can use topological intuitions or properties like compactness and nicely mediate back and forth between these two things. Okay, so let me mention some examples of such dualities. I've already given you a list of examples, but now let me focus on things that really have this mirror image structure. So the first one is vector spaces and vector spaces. So vector spaces are like the letter A. You look at it in the mirror, and they look the same as they were before. So this is a bit puzzling perhaps, but this is an example of something we call self-duality. Things whose mirror image actually looks the same. And Pontryagin duality would be another example of this in the third lecture. The one I'm going to talk about at length today is between Boolean algebras and certain kind of topological spaces called stone spaces. So Stone actually called them Boolean spaces. But fortunately, people dropped that and started calling them stone spaces. So if you ever come up with an interesting concept, don't give it a name. Wait for the community to name it after you. I've mentioned before the state transformer semantics and weakest precondition semantics. This is actually such a stone type duality, complete with the reversal of the arrows and everything. In general, logics and transition systems are duals, and there was a whole bunch of the dot represents all kinds of people whom I can't fit on this slide. So we now understand that logics and transition systems or automata are really mirror image descriptions of the same thing. And many of the things that we call completeness theorems and so on are subsumed by these kinds of dualities. And the probabilistic analog of this is also very now well known. This is essentially due to Dexter-Cozen, following hints given to him by Gordon Plotkin. Dexter will be here in a few days. So this is a connection between measures and random variables, where random variables, roughly speaking, play the analog of the notion of logical propositions, and measures play the analog of the notion of states. In functional analysis, there's a kind of duality between LP spaces and LQ spaces, with a certain simple arithmetic condition between the P and Q. And finally, we have a connection between commutative, unital, C-star algebras and compact Hausdorff spaces. So this is a lot of words, but this is what I will explain at some length tomorrow. Okay, so the background that is useful to follow this series is some basic category theory, which JV assures me all of you now know. So functors, natural transformations and adjunctions, but not anything beyond that. Certainly no two categories. Some very elementary algebra, linear algebra, and very basic group theory. I'll also be talking about rings tomorrow and about Boolean algebras today, but even if you don't know what they are, it's very easy to explain what they are. So the one thing that might be in Samson's language an obstruction to understanding is a little bit of topology. So I'm hoping that people know what is meant by an open or closed set and have at least an intuitive feeling for connectedness and some other properties like continuity, compactness and separation. I will define the separation axioms and compactness, but the others I'm going to assume you know. However, I just like to quote this remark from a book by Paul Halmosh, where he said the reader should not be discouraged if he or she does not have the prerequisites to read the prerequisite chapter. So even if you don't know these things, I think you can get a sense for what I'm talking about without following technical details. In any case, material like this, I think from my own experience of sitting in lectures, I don't follow more than 10% anyway. So I rely on handouts and subsequent reading on my own later on to really get it. Okay. So one piece of propaganda that I do want to push is that maps matter. So it's not just objects that matter, but structure-preserving maps between the objects. And the interesting constructions on objects usually have corresponding constructions on the maps. So this is just a plug for the categorical viewpoint. Compositions are either preserved or reversed by these maps and by these constructions that take you from one universe to the other. And this ability to preserve compositions and also to preserve identity maps is essentially what functoriality is all about. And the important point of functoriality is that it gives you invariance properties, because that's what tells you if I've got isomorphic gadgets here, then the corresponding things I'm constructing there will also be isomorphic in the appropriate sense. And hence it tells you, well, if you want to recognize whether things are the same or different, and it's not easy to do so, perhaps it's easier to make that recognition in the other world. And this is, of course, one of the guiding ideas behind algebraic topology. Where it's often not so easy to tell whether certain topological spaces are homomorphic or not, but the corresponding algebraic gadgets are easy to tell apart. Okay, so duality categorically looks like this. You have two categories called C and D. So there was no hyphen in my two categories. These are just two different categories, C and D. And there is a pair of functors going back and forth, but these functors are contravariant. They reverse the direction of the arrows. So these are really ordinary functors from C to D op. So I will write it in this way. There's some controversy about whether you should put the op in the description of duality, or you should perhaps just say there are contravariant functors between C and D, but I like to write it like this to emphasize that contravariant property. So let me spell out carefully what happens. I have an object in one category, a map between these two objects A and B. All of this is happening in the category C. And then I have this construction, whatever it is, that constructs a new gadget in D corresponding to A and another one corresponding to B. And furthermore, I also get a corresponding map. So I use the same letter as is typical when one describes functors to go from f of B to f of A. Okay, so you see the contravariance, it's flipped the arrows. And similarly, if you start from the D world, you get gadgets on the other side and a flipped arrow as well. Okay? So the interesting thing to ask is what happens if I go back and forth. I start with an A, I use F, and then I use G. I should get something isomorphic to the thing I started with in both directions. Okay, so it's those isomorphisms that really tell you that you have a duality. So formally speaking, a categorical duality is a contravariant adjunction between categories C and D, which is an equivalence of categories. So the right, so there are natural transformations that one has to have in an adjunction. We're going to insist that those natural transformations are isomorphisms. It quite often happens that there's a systematic way of getting those categories by looking at all the objects, all the morphisms from a given object into a very special kind of object called a schizophrenic object. And this word schizophrenic is meant to suggest that this object doesn't know where it lives or what kind of thing it is. It sometimes thinks it's one, sometimes thinks it's the other. Hence it lives in both categories and you can take the maps into it in both senses. And this actually constructs the functor that takes you from one world to the other. Okay, so here's a duality that you already know and love. At least I hope you love it. So this is the ordinary duality of finite dimensional vector spaces over some field, let's say the complex numbers. The dual space of linear maps is also a finite dimensional vector space. And it's easy to show this by choosing a basis for V, then choosing in an evident way a dual basis for the space of linear maps V star. So this shows that you have the same dimension even as V, and that there is an isomorphism between V and V star because they have the same dimension. However, that isomorphism is basis dependent. It depended on my choosing the basis, setting up a corresponding dual basis and making the isomorphism like that. So the double dual, the dual of the dual, is also isomorphic to V. However, in this case we have a canonical isomorphism. So this word canonical bases were harmed in constructing this isomorphism. Okay? You can describe the isomorphism by simply saying, well, if you give me a vector v, how do I get an element of v star star? Well, it has to know how to assign numbers to elements of v star, and the obvious thing to do is to grab the thing and say, apply yourself to v. Right? And no basis had to be mentioned in doing this. So this is in fact a natural isomorphism, and indeed the original paper on category theory gave this as the motivating example to formulate the notion of natural transformation or natural isomorphism. This transformation is not just at the level of objects, as I've said several times, but also at the level of maps. So if I have a linear map, I get a dual linear map going in the opposite direction. And in every instance you'll see that it's very easy to figure out what the dual map is, and you'll be very hard pressed to figure out a map that goes the other way. So kind of the typing of the situation automatically tells you that the only sensible way to construct a map is in the contra direction. Okay, so it's the obvious thing here. I want to construct theta star that takes an element of v star and gives you an element of u star. When an element of u star has to know how to assign a number to u, so now you have those ingredients, sigma and u, and theta. How do I construct a number? Well, sigma knows how to take elements of v to numbers. Unfortunately, it doesn't have an element of v, but theta knows how to produce an element of v. And so there you are. Okay, so now let me get down to duality. So first I'd like to do a toy version, which is the stone representation theorem. We start with Boolean algebras, a whole bunch of axioms here which I don't expect you to read, but roughly speaking, Boolean algebras axiomatize ordinary propositional logic or ordinary set theory with the two binary operations of union and intersection and 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 or in propositional logic. Again, these axioms embody the usual axioms one associates with those things. The important point is that there is also a negation operation in a Boolean algebra and a bunch of more axioms. Okay? You're intended to not look at those axioms, just to glance at them and say, oh yes, they're familiar. So the maps between Boolean algebras are simply the maps that preserve these binary operations as well as the constants and the unary operations. So we're going to make a category where the objects are these Boolean algebras and the maps are Boolean algebra homomorphisms. One important structure that emerges for free from this algebraic presentation of Boolean algebras is an order structure. So you can define a notion of less than by saying P is less than Q if and only if P is equal to P and Q. Equivalently, you can define it this way. Okay? And it's very easy to see that these Boolean algebra homomorphisms can also be seen to be order preserving. So this is actually, though not part of the original axiomatization, a structure that comes naturally with it. So here are simple examples of Boolean algebras. If I take a set and I look at the power set, all possible subsets of that set with the operations of union, intersection, I take the zero element to be the empty set and the whole space to be the top element or the element 1, I will get the Boolean algebra. If I take the regular open sets of a topological space, I get a Boolean algebra. So perhaps not everybody knows what a regular open set is. So those are sets where if you take the closure of the set and then look at its interior again, you get back the original set. And an example of something that's not regular is if you take the open interval 0, 1 union with the open interval 1, 2. Okay, so 0, 1. So this doesn't include the point 1. When you close it, however, you grab the point 1, and then when you take the interior, you still got the point 1. Okay, so these are open sets that are just trying to touch. So regular ones, that doesn't happen. So if you take regular open sets, you do get a nice Boolean algebra. And of course, the motivating example of Boolean algebra, at least what motivated Boole, was propositional logic. So if you take equivalence classes of propositional formulas under provability, then you get a natural Boolean algebra. And for a non-example, if you take all the open sets of R, you won't get a Boolean algebra because complementation doesn't work for you very well. Okay, so I'd like to introduce now a very special kind of structure that might or might not exist in certain Boolean algebras. So this is called an atom, and the word should suggest something that can't be split, and indeed that's what it means. These are non-zero elements of the Boolean algebra, but there's nothing between them and zero. So it's like the smallest non-zero things that you can have. There's no reason why a particular Boolean algebra should have anything like that, but it might. And if it does, that element is called an atom. And so the typical example is, if you go back to the set theoretic Boolean algebra, the singleton sets are atoms. Okay, there's nothing smaller than a singleton set. So a Boolean algebra in which every element can be constructed by taking the unions, or the join more precisely, of the atoms below it is called atomic. So there are a number of different equivalent ways of defining what it means to be atomic. Often this is given as a proposition about atomic Boolean algebras, but I actually find this is the one that's the most meaningful aspect of what it means to be atomic. Everything can be constructed from atoms. So a non-example is that if you take the Boolean algebra generated by the half-closed intervals, you get a non-atomic Boolean algebra. But if I take some discrete set and look at its power set, that's certain, or any set, and look at its power set, that's going to be atomic because, as I said, the singletons are atoms. And certainly any set is the union of the singletons that it contains. Okay? So these atomic Boolean algebras are particularly nice and simple. Adding even more special structure, I'm going to define what's called a complete atomic Boolean algebra, affectionately called a Kaba. So the word complete here means that every subset has a meet and a join. Okay, in terms of the order structure, the greatest lower bound and the least upper bound. So such a thing is called a complete atomic Boolean algebra, and a very easy simple exercise is that every finite Boolean algebra is in fact a Kaba. And the theorem associated with these things is that any Kaba is isomorphic to the set of all subsets of some set with the usual set theoretic operations. Okay, so set theoretic Boolean algebras are always Kabas, but even more, any Kabas looks like that. Even if it's not officially presented like that, it will turn out to be like that. And the proof is quite elementary. You look at the atoms. You take the power set of the atoms and you can construct the isomorphism fairly readily. A little bit of work needs to be done to prove that everything works, but it's essentially straightforward. And in fact, a Boolean algebra is isomorphic to the power set of some set if and only if it is complete and atomic. So this looks like a nice statement. Complete atomic Boolean algebras were described in this abstract way, but it turns out that there are always these concrete things. So you might ask this about general Boolean algebras, ones that are not complete and atomic. Are they always, well, they're obviously not always the power set of some set, but perhaps they're always some kind of set theoretic Boolean algebra. This turns out to be the case. This is indeed the stone representation theorem. However, it turns out to get that correspondence, one cannot just do elementary set theoretic combinatorics, one needs topology. So let me just say a little bit of topology. So this section is called some topology. So the important concept is the kind of topological counterpart of the notion of finiteness, and it's called compactness. So the word cover means you have a family of sets that between them cover the whole space. And an open cover is when everything in your cover is itself open. The compactness property says you try to cover, you cover a space being very liberal with the number of sets you use, you have lots and lots of them. It turns out that it always happens that a finite subset of them suffice to cover the space. So every open cover has a finite subcover. And really the way you should think about compactness is that the space is really got walls around it. It's really, you don't have room to pack lots of little open sets. So there's a famous theorem, Heine-Borel theorem, that says that closed and bounded subsets of Rn are compact. And indeed, in introductory analysis courses, they often use this as the definition of compactness. But this is actually the more useful one in a more general context. Okay, so you can see this notion of finiteness is built in there. Hausdorffness is, so this is telling you that your space has not too many opens. Okay. This property, by contrast, says your space has lots of opens. So it says if you've got any 2 points that are distinct from distinct points, then there are disjoint open sets U and V with X in one of them and Y in the other. So you can really separate 2 points by disjoint open sets that don't even touch each other. Okay, so such a space is called Hausdorff, or T2. This T2 is because there's a full hierarchy of these separation properties indexed by numbers. It's T0, T1, T2, T3, T3 and a half, T4. I think it goes up to T7. But anyway, we often will just say Hausdorff. And this combination, where we have not too many and a lot of combined, gives you compact Hausdorff spaces. So these are spaces that live on the edge, sort of like Bob. If you add more and more open sets, the topology will fail to be compact. And as soon as you remove some open sets, it fails to be Hausdorff. So it's really finely balanced. Okay, and it turns out these ones are closely connected to Boolean algebras. Okay, so let me spell out some of these other separation axioms, and you can see they follow a very natural hierarchy. So T0 spaces are ones in which if you have 2 points, there's an open set containing one of them, but not the other. But it might not happen symmetrically. Maybe there's nothing that contains only that and not this. If it's T1, then you have 2 distinct open sets. Each one, this one doesn't contain that and that one doesn't contain this. However, there might be overlap between them. So T2 says my open sets can be made disjoint. And higher properties is you take a point and a closed set and you can separate them by disjoint opens. Finally T4, 2 closed sets can be separated by disjoint opens. So in many topology books they will tell you any reasonable space is at least Hausdorff, and these things were only invented as counterexamples by peculiar perverted logicians. But this is not true. T0 spaces arise all the time in computer science, particularly in domain theory. T1 spaces arise all the time in algebraic geometry. And so they are far from pathological. It's clear that they form some kind of natural progression. Each one is strictly more stringent than its predecessor. And here are T3 and T4, as I mentioned before. These spaces are called regular and those are called normal. Now, it turns out that compact Hausdorff spaces are automatically normal, hence also regular. This is one of the standard homework questions that you get in your first topology course. Connectedness is an intuitive concept. So you want to say that your space can't be broken up into disconnected pieces, right? And how would a piece be disconnected? If I have an open set that describes sort of half the space and another open set that doesn't touch it, describing the other half, then it's really falling apart into 2 separate pieces. So the way we say this is, remember that a closed set is just a complement of an open set. So if I have a set that's both open and closed, it means its complement is another open set. And the whole space is broken into 2 disjoint pieces. if I take a maximal connected subset, then you get what's called a connected component. Okay? Now it turns out some spaces are as disconnected as they can possibly be. So, so these are called totally disconnected spaces. And these are spaces in which you try to make the connected pieces and you find the biggest connected pieces you can construct are actually single points. So you can't break single points further, but if your only connected components are all singleton, you say the space is totally disconnected. And these occur all over the place. The Cantor set is totally disconnected. The irrational numbers are totally disconnected in the subspace topology. There's another closely related concept called zero dimensionality. Now a space may have a set, may or may not have a non-trivial set that is simultaneously closed and open. The presence of such a thing, of course, is a signal of disconnectedness. Okay? So these sets are called clopen, something which my spell checker is constantly trying to change. But I have to kick it and tell it, yes, clopen really is a word. It means closed and open. And of course, a non-trivial clopen set means the space is definitely not connected. Now, it could be that you have lots of these clopens. So we'll say a topological space is zero dimensional if there is a base for the topology consisting of these clopen sets. So a base for the topology is simply a family of open sets that are enough to express any other open set as a union. So that means not every open set is clopen, but there are enough of them that anything can be expressed as a union of these clopen sets. So this is another signal that the space is very disconnected. And now we have this theorem that says for locally compact Hausdorff spaces, total disconnectedness and zero dimensionality mean the same thing. So for our setting, we just take these things to be equivalent. Okay, so I've introduced some topological concepts: compactness, Hausdorffness, and zero dimensionality or totally disconnectedness. Okay, so compact Hausdorff spaces are totally disconnected if and only if they are zero dimensional. So finally, we're going to make this a definition. A stone space is a zero-dimensional compact Hausdorff space, hence totally disconnected. Okay, so this was a long digression into apparently into topological concepts that seem to have nothing to do with Boolean algebras. But it turns out these are the mirror images of Boolean algebras. And when you look in your duality mirror at the category of Boolean algebras, you will see stone spaces. Those of you who've done a little bit of algebraic geometry may have come across profinite groups. So this is a canonical example of a stone space. Now notice one thing that might signal that this is something to do with Boolean algebras. Clopen sets do form a Boolean algebra. Remember I said if you just take the open sets and naively just take the complement, your open set is going to become closed, it's not even in the same space. But if I look at the clopens, then complementation will take me from clopens to clopens. So, Boolean algebra structure is there somewhere. Now, we're going to make a category out of these things. The objects are stone spaces, and continuous maps in the good old topological sense will be the morphisms in this category called stone. So I'll just mention a useful fact, which I won't actually use, but if you want to prove any of the things I'm saying subsequently, this is useful. A continuous bijection from a compact space to a Hausdorff space is always a homeomorphism. This is also usually in your first topology course problem set. Okay, so it's not obvious at first sight, but you just start playing with the definition for a few minutes and you'll see it. So in particular, this means continuous bijections from a stone space to a compact Hausdorff space is a homeomorphism. And hence maps clopens to clopens. So you see it's preserving the Boolean algebra structure that's hiding inside the topology. So here's the grand theorem. You take the category of Boolean algebras and you take the category of stone spaces opt appropriately, and there's a way of going back and forth between, I guess I should say forth and back, from Boolean algebras to stone spaces. So I just need to tell you what these two functors are. And this name, you can guess, it stands for clopens. I'll say take the clopens of my stone space and I will get the Boolean algebra. And now I'll tell you what this is. Okay, so let me say a bit about filters and ultra-filters. So a filter, I find it useful to think in terms of coffee filters. They are so remember Boolean algebras are ordered, so there's some kind of ordered set, and the filters are the things that look like that. They're upward closed. If anything is in the filter, then anything above it is also in the filter. And if you have two things in the filter, then their meat is also in the filter.
Is that why they're called filters?
Yes, yes, they look like coffee filters. So, not sure what ideals are called. Ideals. Right, so this is just the algebraic statement of what I said in words. An ultra filter, at least the word sounds impressive, in a Boolean algebra is a filter such that it's as big as it can possibly be. So if you take any element of your Boolean algebra, either B is in the ultra filter or the negation of B is in the ultra filter. Another way of saying this is it's the maximal possible filter you can have. Okay? If you try to enlarge it any further, you'll get the whole Boolean algebra. Okay? Now it turns out there's another way of looking at these ultra filters, and this particular correspondence between these kind of maximal filters and homomorphisms will be also very useful in understanding Gelfand duality tomorrow. So, if you take a Boolean algebra, we can construct a very nice Boolean algebra called 2. It's called 2 because it has exactly two things in it, the two things that are required to be there by the axioms of Boolean algebra, namely a bottom element called 0, a top element called 1, and nothing else. Okay, so that's the Boolean algebra. The order structure is 0 is below 1. And if we look at it, you can look at homomorphisms from your favorite Boolean algebra B into 2. And if you look at the inverse image of that top element, you will always get an ultra filter. And furthermore, if you have an ultra filter, you can always construct a Boolean algebra homomorphism into 2 by mapping everything in your ultra filter to 1 and everything else to 0. You can check that that's always, so there are two ways of looking at ultra filters. Either you can identify it with its homomorphism, or you can just think of it as a subset of the Boolean algebra. And both views are important. It turns out this two-point space is confused about its identity. Okay, so we've just presented it as a Boolean algebra. It's also a discrete topological space where the open sets are, everything is open. So the singleton 0 is open, the singleton 1 is open, obviously the whole space is open, and the empty set is open. That forms a nice little Boolean algebra all by itself. In any case, this is a topological space with the discrete topology. So, let B be any Boolean algebra. If I look at this space, the space of all functions from B to 2, arbitrary functions, not even required to be homomorphisms in any way, and I give it the product topology, I get a stone space. So this is of course just a big B-indexed family of products of copies of 2. And it's a theorem that says if you take even big products of compact spaces, the result will be compact. This space is easily seen to be Hausdorff, and one can verify that it's actually totally disconnected. So it's totally disconnected because the basic clopens turn out to look like this. So you take any finite subset of L and you assign arbitrary values to the elements of L, and then you look at all the F's that agree with this function delta defined on your finite subset. So any such set gives you a basic clopen set for this product space. Okay, and so you could get, now supposing I say, all right, I had any old functions there that I wanted, now I'm going to say no, look only at the homomorphism. So now I'm imposing an algebraic condition So I'm looking now at a subset of 2 to the b. You can show fairly readily that this forms a closed subset, and hence is a stone space in its own right. So this is the stone space that you construct from the Boolean algebra. So you constructed a stone space from a Boolean algebra by looking at it as homomorphisms. But remember, these homomorphisms are ultrafilters. So we can identify S with the space of ultrafilters of B. So this is another way of presenting this space. How do I go back? Well, if I have a stone space S, it has a base of clopin sets. So I just take my basic clopins, and they will give me a Boolean algebra automatically. So the clopins of S correspond to the elements of B. Of course, I'm not saying that all opens are clopins, but if I do look at the clopins of S, they precisely correspond to the elements of B from which I started, and that clopins note always form a Boolean algebra. So I'm back in the Boolean algebra world, and this collection, this stone space that I got from B is called the dual space of B. The Boolean algebra I get by looking at the clopins is called the dual algebra of S. And these two constructions take you back and forth. So here is the grand isomorphism theorem. If B is a Boolean algebra and S is its dual space, and A is the dual algebra of S, then B and A are in fact isomorphic. If I start from B, go to S, come back, the thing I get may not look like B, but it will be isomorphic to B. Okay, so they'll be isomorphic as Boolean algebras. And similarly, if I start with the stone space, look at its dual algebra, and then construct the dual space in the way I described, by looking at the ultrafilters and topologizing it, then I get something that's homomorphic to the original topological space. And this proof actually uses that useful fact that I alluded to earlier to construct a homomorphism. And these things are supposed to be functorial, of course. So what does the arrow part of the CL functor do? So it goes from stone spaces to Boolean algebras. So if I have a function from x to y in the category of stone spaces, these are continuous functions, I will define the action on the arrows as F inverse, which of course takes you from clopins to clopins. Inverse images of open sets are open. So you see, the inverse image is the natural thing to construct. It's very hard to construct something in the other direction. So in the contra direction, standard topology tells you this is the thing you should be looking at. Similarly, I have this ultra-filter functor. I haven't yet made it a functor, but I'm about to. That goes from Boolean algebras to stone spaces. So supposing I have a homomorphism between two Boolean algebras A and B. I want to construct a continuous map between the space of ultrafilters of B to the space of ultrafilters of A. And I want to do it in some simple. The important point is that these are not fiendish constructions. They're always natural, simple things. So what's a natural, simple thing I can do? Perhaps not obvious what to do with an ultrafilter, but it's actually obvious what to do with a homomorphism. And of course, we know that these ultrafilters are nothing but homomorphisms into two. And what's the obvious thing to do with a homomorphism into two? I'll just compose it. I have a homomorphism G going from B to 2. I have this homomorphism from A to B. I just put them up, and I've got a homomorphism from A to 2, aka ultrafilter of A. So I've gone from ultrafilters of B to ultrafilters of A. Again, natural, simple construction. You would be hard-pressed to imagine something going the other way. So this is functorialized, the definitions I've given before. And now I can actually state the grand stone duality theorem. So if I take a stone space S in algebra B, then there's a natural bijection between these Hom sets, BA like that and stone like this. So these are Boolean algebra homomorphisms from B to the clopins of S. These are continuous functions from S to the ultrafilter space of B. Okay? You might be a little bit puzzled by this because both these things are on the other side, but remember it's actually stone op. So if it was stone op, it would be like that, and now you can see you really have an adjoint pair. Okay? In fact, we have an equivalence of categories because the natural transformations that are required to be there associated with the adjunctions are in fact isomorphisms. Those are nothing but the isomorphism theorems I mentioned earlier. Okay, so that's the Boolean algebra topology world. You can either argue about things algebraically in the Boolean algebra world, or you can go to the topological world and perhaps use compactness properties or disconnectedness properties on the other side. So just to wrap up, let me say a bit about schizophrenia. So this thing too, as I mentioned before, it's a two-element Boolean algebra, and it is also a two-point topological space. In fact, it's a stone space because it is totally disconnected. Okay, and if you look at the Boolean algebra homomorphism from B to 2, you get the ultrafilters on B. If you look at the continuous functions from S to 2, you get the clopens of S. Okay, so you see that in both cases these functors are realized by looking at maps into the schizophrenic object. And many dualities are mediated by such schizophrenic objects. We will see this in the third lecture on duality for groups. So some extensions. So one of them is when you go from Boolean algebras to a more general thing called a lattice, where you don't necessarily have a negation operation. So here, instead of looking at ultrafilters, we look at prime filters. So a filter is said to be prime if this join is in F, then one or other of them has to be in F. So unlike in Boolean algebras, prime filters are not the same thing as maximal filters, which is what we define ultrafilters to be. However, for certain distributive lattices, then indeed we can use prime filters and maximal filters interchangeably. And we define something called the prime spectrum of a lattice as the collection of prime filters of the lattice. You can make this into a topological space, but in fact this topological space comes with a nice order structure of its own. So this was constructed by Hilary Peaslee here in Oxford. So she defined a new topology on the prime spectrum of bounded distributed lattices, which is both compact and Hausdorff, but there is an order structure that plays a crucial role. So you define a Priestley space as a compact ordered topological space where the clopen downsets, now that you have order you can talk about sets being downsets, separate points. And you get a duality theory between these spaces and bounded distributive lattices, which I think is probably the most general, purely order theoretic kind of duality you can have. So you remember I told you that the most disconnected you can be are these totally disconnected spaces. Well, I lied. It turns out there are even more disconnected spaces called extremely disconnected spaces. So we're going to define a compact Hausdorff space to be Stonian. This is very bad terminology because I got confused when I first saw this. I thought, this book written by a foreigner, he doesn't know that it's called a stone space. And I wasted time trying to prove that these were the same things as stone spaces, which they are not. So they're called Stonian spaces. If the closure of every open set is open, weird property. So you're closing it, you get the smallest closed set containing your open set that you started with, and the thing you get is still open, and hence obviously clopen because you just constructed it to be closed. Okay, so these spaces with this property are called Stonian spaces. And you can prove that every Stonian space is in fact a stone space, but not vice versa. There are examples of stone spaces that are not Stonian. And who cares? There is a duality theory between Stonian spaces, the category of Stonian spaces, and complete, but certainly not necessarily atomic, Stonian spaces and complete Boolean algebras. So this particular duality is important in the theory of C-star algebras. Okay, so I couldn't actually write down a nice example of a stone space that's not Stonian, but I'm sure they exist because of course I know that there are Boolean algebras that are not complete. So the dual space will indeed be an example of a stone space that's not Stonian. So anyway, there you are. we have Estonian spaces as giving you yet another closely related duality, this time a more restrictive one. Okay, so I think I have finished. Yes. Okay, thank you.
Thanks, Prakash. Any questions for lunch? Yes, Chris?
Do you happen to know to what kind of Estonian spaces complete and atomic Boolean algebras correspond?
Complete and atomic. So those are, we should describe them as Estonian spaces. So those are the power sets of the atoms.
Do they have some nice topological property?
Yeah, they must be discrete. Samson is muttering in my ear that they're not very interesting. But yeah, they're surely discrete spaces.